Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, thank you for coming. I would like to introduce Eric Newman. I met him a couple of years ago at BioIT World and got to get an understanding of some of the work that he is doing in Semantic Web. Last year, I think, or maybe a little before, you came out to talk to the SQL Server group, and that was a very productive discussion. And last April, he invited me into the Healthcare Life Sciences group, where I happened to sit down. I think I may have elbowed somebody out of the way, but I happened to sit down next to Tim Berners-Lee. And for the first time really understood sort of the simple, powerful idea of being able to understand what happens out on the web and how to put that together. So Eric has agreed to come and give us an update on where things stand in the healthcare life sciences. He is also executive director of, a little commercial plug, executive director of the Clinical Semantics Group. Eric?
So thank you very much, Don, for inviting me. Really looking forward to talking to you again and talking to you as well. I'll be honest from the beginning. I'm an evangelist in the semantic web. I've been pushing it for about 8 years, but I'm originally a neurobiologist. So any evangelism is coming actually out of what I think are productive and useful approaches to using information from experiments and research. And these days, you know, there's so many different forms of it. So I'll give a little bit of history on the healthcare and life sciences group. So the semantic web idea started, actually, if you look at the earliest quotes, they come out of Vannevar Bush's article, which actually was in the Atlantic Monthly. You know, we'd think it comes in some sort of scientific journal. It was something he wrote in 1947, 48, on Memex, which is, you know, a real digital library of knowledge, not just the facts, but even understanding. So he doesn't talk about concepts and nodes and semantics, but you can see he's thinking that abstractly. He's even way ahead of his time with the whole artificial intelligence view. And a lot of people picked up on it. I used to work at Bolt, Brannick and Newman, and that was a theme too about how to use semantics and stuff. But you know, there was the high-powered, funded by DoD type projects, and then there was the public. And the public's never going to be interested in timeshare systems and stuff. You know, that's who needs a machine to figure out the trajectories of missiles and stuff. That was the angle back then. But what happened was the internet came, which BBN had a role in, and then the web came, which was another way of viewing how information becomes accessible to humans. And as Tim Berners-Lee put together this, you know, first rudimentary form of exchanging information for humans to connect. And if you look at the history of it, if you read his book, he describes it when he was working at CERN. There were researchers who did all sorts of different physics projects, and there's all sorts of electrical engineering that had to be done in this place. And they would only really discuss when they would go to this coffee shop, which was at the junction of these two hallways deep underground, and they then would exchange ideas. And it was apparent that this doesn't happen enough. It's happening in the physical world, but these guys are already using email. Why isn't it, you know, a space for discussion happening there? So he had proposed, you know, a simple model in his view for documents to be pointed to and referenced from within documents and how it would work. But it would be decentralized. It would have fault tolerance. If you don't find the page there, it doesn't break. And it's just a matter of a common protocol that can work across all the different DNS sites. But it was clear back then that even though we're exchanging documents with little tables in them, it would be great if the data itself was well connected. And back then it wasn't. So he had always thought that, well, if this thing really does take over, you know, and grows, maybe we'll get a chance to go into semantics one of these days. And you know, in the time span of 15 years, the money for physics has obviously gone down a bit, but in life sciences and healthcare, it's been going up. And in discussions we had back in the late 90s, we thought that there's so much complexity to the kinds of data and the understanding of life sciences that's out there that continues to grow. This would be a really cool test case, a test environment for the semantic web. And so We discussed it for a couple of years. In 2003, we put together sort of an initial discussion group on it with Eric Miller, who was then the lead for Semantic Web at W3C. And we thought, well, even though working in life sciences is a domain, you know, it involves people that know biological science, but maybe not anything related to first-order predicate logic, it might be interesting to see if these guys can come up with use cases and even demonstrations faster than the techies can. So we made it, we formulated the first domain-specific interest group. And interest groups are not necessarily charged with coming up with standards like a work group does. So we don't put together an XHTML format or an XML or SVG. We're talking about how the current standards can be used and where there might be deficiencies. And we thought, well, should we do it for this group, for the academics, for the pharmaceuticals? And we decided to do across the board. So that produces its own challenges, because you will have people who are really into sort of the understanding of the, you know, how genes interact. And then there are companies who are only interested in that aspect of genomics that has a direct implication in developing safe and efficacious drugs. But we are seeing the world starting to connect anyways. And so it was a good plan to really integrate all these different efforts together. That was chartered for 2 years, and we are now rechartering the group for another 3 years to continue. We've brought on lots of different groups of people, and there are a lot of projects. I'm going to talk about a handful of these projects and the kind of questions people are asking. So sometimes people ask, what is the semantic web? And the problem is, there's so many different ways of saying, you can talk about the technical aspects, you can talk about forget the technical side, how does it change human society? You can go forever in any of these directions. So in this talk, I'm going to focus really on applications in life sciences that have been identified as really big, grand challenges. And some of them that are now being actually addressed and not completely solved, but we're seeing inroads to things that we've been talking about for so long and nothing has happened. So there's some very promising things going on. So let's see if I can use this right. The first thing to think about is, let's look at the connected model of all of life science research and healthcare. And with some credit going to Tim's original London Underground model, this is a view of the different ecosystems and the paths that each of the different systems have together around the world. And the way to view it is that every colored line you'll see is coded with a different organization or group of organizations. So biomedical research, which is academic and medical. You have the pharmaceutical groups. You have healthcare providers, HCP here is in blue. The insurers, someone's got to pay for it. The public, who's actually being treated and is contributing to the payment too. And this thing sticks together and is constantly changing too. But the current view is information that is gained in different parts of this should be somewhat available. You know, it's people have taken the time and paid for it, for work in different areas. So a lot of basic research on how, you know, biology and genes work is important in eventually getting up to here, where you start to come up with what's the best treatment for diabetes type 2, and, you know, what's going to be cost effective. Early, you know, prevention. Do you segment the population for those people that are higher at risk? So that stuff has been talked about over on that side, but it's not happening yet because no one understands the economic impact of it. And when you get down to a lot of the problems, it's because, well, we can't take the information from this group and apply it here. There's a real problem of the ideas and the stuff going on there can't be linked cleanly. They're discussed in paper after paper that gets published in, you know, JAMA and also in Nature Publishing, but there's no knowledge that's really truly connected to make, you know, insights. And there's so much being published in any field now, not one researcher can really understand the field completely based on the current rate of papers being produced. Aha. So now we're really going to have to rely on various algorithms and tools that index and identify things and provide, you know, as an assistant, what is out there and what you need to know. And we've hit, the numbers are pretty astounding. There's like what's the one that Larry Hunter points to? Every year in a certain field, there's like 120,000 papers published. And so that, you know, it would take you the rest of your lifetime just to read what's produced in the grander field in just a few months. So we're losing out. The scientists aren't able to catch up with us anymore. So it's information, and the stuff we produce is becoming massive. And the way to think about this model, if you remember the original the London Underground model, the threads were like different applications. There was mail, there was calendar, there were various vendor-related tools and stuff. And each of these needed bits and pieces of the different information coming from the email and from the calendar and from when the meeting was being held. And the notion was that every point that there needed to be some sharing across these different applications, you put a little circle, that's like a station at a subway. And so if you want to get here, you basically take it to one of these stations and get across, and you just take everything with you. And so the same theme can be ramped up not just from applications sitting on your desktop, but to the entire industry. And the notion is that the data, which could be one small packet from one study or one individual, or it could be everything known about diabetes, would be somehow able to be taken across these different bands. And of course, these days you don't have to move a lot of data around, you just have to have a pointer. And the idea here is if you index things and you index them with the right sort of metastructure, you have a very lightweight way of carrying things as you need them across. And so things get together and go apart, sort of like trains do. They can connect and they can disconnect without breaking the semantics. And that's sort of the vision behind this. So the regulatory agencies are able to align with the efforts from pharmaceuticals as well as what's going on in clinical research. And these are the areas that would all benefit from tighter interaction with each other. So this is, a bit of a vision, a little bit of a roadmap, and sort of the philosophy of what the semantic web in life sciences would be like. And I should have pushed this before. These are all the various silos of data. Each one really is many, hundreds of different databases. This is one that has been produced for the FDA for looking retrospectively and prospectively at your clinical trials. So that, prospectively, of course, you want to get your drug into the market, you want to show it's safe. But retrospective, so the FDA can learn from all the past projects and say, we see a pattern here, and we can actually suggest efficiencies because we see this trend over and over again for this class of drugs. But it's a classic relational database model with a lot of tables and interconnections that look at findings and events and studies. How that's all going to get cross-connected, no one's thought about that. And there are efforts for standardizing, but my point of view, which is biased, I feel that a lot of the standards efforts that we're currently working very heavily on that may be implemented, just may be implemented in 3 to 5 years, still won't allow this type of connectivity. And interestingly, if that is the only effort out there that is being built for the industry and for the government, I bet you the Web 2.0 folks will beat them. I'm positive. And that's an interesting view of it, that if they do reach out to the public on this and the public finds their access to information about disease and they can have their accounts, and that might just take over what's already out there. So there's interesting dynamics starting to happen right now, and several high-profile clinical researchers at pharmaceuticals are actually leaving to start their own little startups on this. So where the semantic web fits in that, I don't know, but there is a dynamic of change occurring across this model. And one of the buzzwords you'll see me mention again is translational medicine, which effectively means trying to translate the knowledge information from basic research very rapidly into the clinic, into the bedside. And it means also the clinical studies go and talk about what's the next set of experiments to look for better treatments of cancers and stuff like that. So yeah, that would be a great vision if all this stuff was really easily used by all the different institutions. And it is being pushed by the NIH in their roadmap as well as the FDA. You'll see this word come up as translational science and translational research, but it basically means really effective knowledge use. So from a healthcare provider, Partners Healthcare is one of the largest healthcare provider groups in the Boston area. They have all of Harvard Med and Dana-Farber. And the head of research there had placed these bulleted items that are what are the challenges in the informatics space when there's so much need. So first, what you see is that innovation, getting into practice, is just horrific. It's at a slow pace. There's nothing suggesting it's going to go any faster. It takes 17 years. The other thing is that we're talking about really basic things that would allow people to have more directed, appropriate health care, right? We keep talking about personalized medicine. Just appropriate care would be, an improvement. And you've got a 5 to 10% chance in any hospital you go to that you're going to have an adverse event, meaning they're going to give you something. It can be something as simple as blood thinner like warfarin, and you're going to have an episode. It happens a lot. And it's because not any single person's the same with the average. Everyone is different. And the treatments are about policy. And if someone starts to react, you titrate the medicine quickly. But capturing these events is something that there's better ways of handling this, including diagnostic technology and chips, which is also struggling to get into the mainstream. The other thing is, okay, where's all this money coming for real changing of the industry? There's no direct benefit obvious. So who is going to really support this? All these new diagnostics for, is this the right way to treat this particular person? There's got to be a reimbursement mechanism. It's that basic. And there's no structure, either coming from the government or coming from the commercial sector, saying, yes, we need better technology and things in place because it'll eventually make things cheaper and safer. No one wants to take that hill climb to find the lower point. So everyone is balking. And when you say, we need this technology, but it's going to take us 5 years to develop, and it's sort of like the space shuttle project, no one's moving. We're not taking advantage of the knowledge. Electronic health records, EHRs, are been talked about for a long time. Currently, every hospital has their own sort of version of it, but they aren't standardized or able to be cross-connected. So the really question is, we're not really able to put good current technology systems of knowledge and policy checking into place, even in a big place like Harvard Medical. So, where is this all leading us? And that, as I said before, the velocity of knowledge that's being produced is massive. What part of that is going to have to go into the hospital to say, this is the current view of treating anyone that's over 55 with obesity? That's going to change very rapidly, and there's no system that you can update the rules without writing a lot of extra code. So that's prohibitively expensive, too, in most circumstances. So they're seeing this is the current state of things, and it's going to be very painful to get past that. Yes? Clearly. A big question is if a certain class of diagnostics do get cheaper, and they will. There are chips that are going from the 10,000 mark to under 1,000. Yeah, it'll start to happen. And then people will get a better sense of confidence what can be done. Then there'll be a demand like, why don't you use this so that I don't have an adverse event? And the public opinion changes too on this. That'll help. But we're not at that delicate point where the public realizes there's value gained, and the hospitals don't know whether it's going to be accepted or not. So the tripping point hasn't been met yet. Well, they're going through channels because they thought there's so much big money in healthcare, but they don't understand is even though there's big money, the margins can be so tight, no one's going to take the risk for it. So Affymetrix and Roche, which have these new P450 chips, didn't put into the equation how long it's going to take to convince them and the insurers to buy into this technology. So they're like 5 years behind now because of that mistake. So another problem, this is again very genericized, there's silos of data. They've evolved differently over time. And yet more and more of the stuff we want to try to connect. So in pharmaceutical companies, we have this problem. In basic research, we have it between all the different research organizations. NIH, everyone has it. So a federated approach is very, very difficult to do. It's especially difficult to do if you've got legacy. And the other thing is if you want to make one super relational database that has, there's many more flavors of data out there than that. It's really difficult. So no one can afford it, not even the pharmaceuticals. And the other thing is every time they come up with a new screening assay, do you think they update the old stuff and then put the new stuff in there? No, they just build another database and with a little bit different structure and then they drop in there. So you've just generated yet another piece of complexity of the puzzle. So that's the trend, and it's getting out of control. So going back to what we'd like to do with information, and I think some of these are self-explanatory. If they're not, feel free to ask questions. So we'd like a common way to link data and documents together. And I mean link is the humans feel they're linked, and it's also linked in the way that the machines can find information, right? Linkage is both a human as well as a machine-based approach, and especially across these databases. We really would like to reuse data. Even though the data was captured for this particular study, it would be stupid not to be able to reuse it for a related study, even though it's slightly different. And reuse doesn't necessarily mean we have to like reformat the data to be put in that. There may be a way to have data in a structure or representation where it doesn't have to be continuously changed, but it can be used pretty much in its current form, and added value can be linked to it. The ability to annotate, to say something about the data. If you don't think annotation is big, just look at the whole blog phenomenon. That's an annotation mechanism. But we need to annotate not just what someone thinks about this movie or this celebrity. It's about the genes and the diseases that people are studying and the drugs that are being applied. We need to find ways that are going to work across the board for access and discoverability of data. Access is being able to get to it, and discoverability is, I don't know it's there, but I need to find something like this real quick. And it can be IP, not just science related, so it has a lot of legal implications. And then blending of, this is a big thing you'll see, phenotypic to genotypic matching, which is work that many of us have done. I have one study that I'll refer to. So the question is, after all this is done, is this data integration or information integration, or rather aggregation? And what are the difference? So information integration had been described by many companies as being able to bring all these pieces of information together in a well-structured form so that you can produce queries and searches on the entire ensemble. But what if you don't have everything in one place, but you can still get to it and bring it together as you need to? Then we refer to aggregation. And I think the term you're probably more familiar with than aggregation is mashup. So here's an integration, overly simplified sketch, pulling things from many different sources into one repository, one identified location, and then you have a couple very well-defined applications that are designed to work with it. And maybe you can create some new ones, but you can't just create them at will because it depends on how it was structured. So if you left something out and you can't have application number 3 developed because it's missing that, it's awfully difficult to go in and fix that later. An aggregation, the idea is that you could pull things from different sources to produce various structures and intermediaries. And you can pull them together in different ways. But the real question, which is, I think if you've played around with some of the mashup stuff, if you've got geolocation and you have some other basic information, that's sort of self-explanatory. But when you've got lots of rich semantics, you can put it together into a view or a table, but it's not going to be really reusable. You do it once, and then when you're done, it's thrown away. So it's not really consistent and reusable. So the real question is, can we aggregate and make sure there's value in it, so that if I've taken the time to aggregate a lot of interesting facts, when I make that bundle a piece of knowledge that gets put in some location on the web, other people can immediately find value in that. They don't have to reformat it. It's got everything it needs already described. And that's the challenge of aggregation, I think. So I don't know if this is going to be a little bit overkill. Maybe some of you are familiar with this already, but I thought I'd do a quick sort of run over of semantic web stuff, and then I'll show it in light of life sciences. So this is the web. This is the web as the machines see it. It's just nodes and blah, 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 connected to blah, 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 connected to blah, blah, blah. And you can mine the text and try to find statistical associations and stuff, but that's cheating. The web itself has no innate meaning. It just has a topology. And it's very useful still. I mean, look what it's all been possible with that basic idea in the back. It's pretty impressive that gets you quite a bit. But the semantic web is using a new standard that works quite similarly on current structures and servers. But basically, you now have typed information as the nodes. And then you have these arcs are actually now, you can think of them as verbs or adjectives. So you can actually have relations between clinical studies and the design of the study it's using, or the subject that it has, and all the different treatments that are done to it. And you look at that and you start to wonder, now, is that in one spreadsheet, or is that in a couple tables, or does that go across multiple databases? And that's the idea of this, is that it can be completely distributed. It doesn't have to sit in one place. But when you pull it in, when you aggregate it, you have a structure that you can do a lot of stuff with. You can query it and view it and ask more questions and fish out more stuff. So it is very connectable. And if you wanted to connect more things to these things, based on your rules and policies, you can. So it's like Lego bricks. You start to connect them. So the structure that lets that happen is this RDF stuff. And just for the moment, RDF, don't even think has anything to do with XML. Doesn't even look like it. It's just a notion of saying this thing is connected to that thing by this thing. It's a triple. Those things are connected by this intermediary. That's all you have to remember. And the other thing is that it's machine processable, so it's not just a string for humans. It's actually a well-defined entity, a URI, which is the identifier scheme, for everything. So you are talking about very specific nodes. If you have a particular adverse event, if you've done this right, no matter what part of the company you're in, or even if you're partnering with a company, that is one node, no matter where you are in the company. It's one well-defined node with all the descriptive information about it. And it could actually pull its content from a database, but it has a well-defined structure now. Most of the semantic web is really built of these layers right here. So from the identifiers, XML, RDF, there are versions of this layer cake that actually have this pushed aside and this going down here. There's been a lot of monkeying around. Different people have opinions. But this is what I was just describing. This is the RDF layer. And above it, we see some areas that are just newly created. We have a query language that's about to be a recommendation. It's a candidate, but it should be a recommendation within the next 3 months. The ontology language, which is amazingly similar to RDF, but it talks about concepts. And the simple schema, which is sort of, if you don't want to do full OWL, you use this to describe your data, and rules, which allow you to make representations and conditionals on the data itself. The stuff above this is very interesting, esoteric, but it's the long-term vision of how that is to be used. And you can see that trust and being able to encrypt things is a very important element of the scheme, too. A lot of people need to know that that's been considered as part of it. But we'll focus really just around this section right here. And here's a classic case of saying this gene. Yes, go ahead. So integrity, if it's well formatted, that's just a simple RDF syntax of triples. If it's validated by logic, you use these two systems. That's the way to say, indeed, this relationship is valid under this or that ontology. So it's an important feature to remember is your RDF can actually reference many constraint languages. So you might be using something from NIH that has a subset of 5 ontologies. You're going to do something very special. You create your additional ontology or schema. You insert that into the prefix clause. And now in addition to the statements that were valid with the original set, you can make new statements that require that and your set to work together. And it's perfectly valid. So you can incrementally increase the statement types, the relations. And yet when you look at the entire structure, you know which ones were valid from NIH and which ones only make sense to you and your partners. So there's it's called namespacing. So you can keep track of all the different formats. It's similar. It's not the same at all to having multiple DDTs in a document. But now it's not about structure. It's about the semantics. Right? So here's a case where we talk about a particular gene called PARC1, which really does exist. It's a subject, a URI. And it has a relationship called has associated to the disease, which the disease is also a URI, Parkinson's disease. So this is defined maybe in SNOMED and resides in places like UMLS. This is in one of many databases like EntreGene. And in the future, they would have a nice URI, so it talks about that particular entity and that record about it. And this is, even though it looks like a piece of text, it's a URI as well. It's well defined in some ontology, let's assume. So here's your triple, subject, predicate, object. And there's nothing really that magical about the structure. But I can make series of these statements. So this is a list of triples. And it could come from one document. It could come from 3 different databases. But let's say we've grabbed a whole set and we've aligned them like that. Now, if you look at that, you'll see there's some redundancy. And the first thing you do with redundancy, or if you're a semantic web browser, without writing any code. So what you see happen here requires no code to be written in addition to anything that, like a browser that exists currently. The unique identities of maptt collapse, you can see, into one node now because it's the same thing. And the same with the diseases. They collapse down to this set. So you have a graph. Now, you can think it through, but if I change the order of this, would this graph change in topology? And that's the advantage of the semantic web sort of format of syntax, is that as long as I've got the same set of triples, no matter how I put them together, in what order, the list order is independent, the topology produced is identical. And that's a fundamental feature of the semantic web's open world model. If you bring in new knowledge, of course, you've got more stuff, but it's monotonic. You've just added more graph elements, and there's more to do inferencing on. So that's a simple way to view it, but that shows you even in life sciences how you can make associations between this disease and that disease through this mechanism of genes. So implicit in that is actually why biologists might think these two diseases are related. See? Yes? Well, they indeed are. So even though there's an arrow, there's always inferred a reverse arrow. Now, you may not have a label for the reversed arrow. So the usual trick you'll see is a little like caret done in front of the predicate, which means go the other way. But in OWL, you can actually define the inverse function. So there is actually a piece of text that says, you know, disease is caused by the gene. So you definitely have bidirectionality, and there's a directional element that's in there. Now, the triple order is whatever's the first thing in that triple, then that predicate is viewed as that's the domain and that's the range. That has to be. Unless you use the other term, which then it's going to test for the reverse order of that. But it's very important that the triples are ordered. But the ordering of the triples doesn't matter. So again, pulling this stuff together from sources has a nice little function. And being a biologist, a couple of us came up with the phrase recombinant data. And it's because if you can pull data from many places, it's sort of like taking the different chromosomes and swapping the different genes. And everyone knows that that's a real powerful feature for higher organisms to get complexity. So we can pull in from different sources. As long as some of these circles are the same identifier, then this step happens naturally. But once we've got this, we can then say, but I've got a great set of statistical viewers and specialized viewers for my customers that show different aspects of the data. So this is your mashup and your dashboard right there. So being able to find them and pull them together is one set of steps. And then once it's here, you can manipulate, you can analyze the entire system at once, or you can feed out different slices of it. I mean, that's how you do pivoting, basically, in RDF. It's not that much more complicated. And just one thing to say, too. These edges, are preserving semantics. There are obviously places where, depending where the stuff came from a study, there might be certain things to be said about the gene. If you rearrange it and you have that statement of the gene, but you have a completely different study, you might have an inconsistency. So there are things that need to keep the context framed so that when you make these different views, you know what the conditions were. And that's really up to still the people who develop the right tools and viewers that you don't lose it. You can always mix sample numbers and stuff and sample sets to screw up statistics, and that would be bad. So you stick to certain principles and practice, and that would apply here too. So even though the semantics are preserved between these, the context of groups of semantics you may want to have really very tight coordination on, especially if you do clinical trials. Semantic web can be viewed as sitting as middleware. You've got a lot of legacy things out here in databases, and they change. There's this ability to make a web out of all this stuff, and then there are tools and browsers that can use it very openly and easily. And so this is what you can do your querying, you can manipulate and view things, you can add and annotate. It's represented in some common way using the RDF model and some other types of storage systems that support RDF, and then it may be pushed back into a variety of different storage systems. Note, spreadsheets, documents, and databases are prime candidates for the semantic web, meaning we don't change them, we just use them. So here's an example of a project, sort of state-of-the-art, what is being done with large assemblies of knowledge from different sources. And this is studying a series of cardiovascular disorders. And this was done with a group at University of Cincinnati. Bruce Aronow is the head researcher of this group. And with Devada Chandra was a graduate student who just finished his degree. He defended his thesis in November, and he started at Lilly on December specifically for this work. So it's already 2 pharmaceutical companies wanted him to do this full time in their company. And Lilly is a very strong active participant also with us. So here you go, you get your genome databases that are out there, and you've got ontologies connected to genes. How many of you are familiar with Entrez-Gene and Go ontologies and stuff like that? All right, so a few of you. And this type of stuff everyone parses over and over and over and over again, yet again, yet again, yet again. And that's fun. You do it the first few times and say you've got a paper, but then it gets boring after a while. So it would be nice if there's a standard way it stays connected. Pathway information, there's not 1 but 4 different pathway resources that are used, and each one focuses on something different. So that's the genomic side. On the phenomic side, you're looking at all the symptoms associated with diseases. And there are diseases in human online Mendelian index of man and the syndrome DB that have been identified, and mammalian mouse diseases, because mouse is a great model system for diseases. And the question is, how can we connect between these two? So, for instance, one of the problems is the text out there has got phrases like aortic coarctation or coarctation of the aorta, and that has to get unified. And you can do that pretty nicely with a tool called MetaMap that comes from NIH, National Library of Medicine. But then what we do is we find the concepts in the UMLS. These are concept unique identifiers, and that points to that node. It's very much along the thought of the semantic web. And then these two have one common place that talks about an aortic defect. So we can take lots of very specific things and we can start to cross-connect them, which you'll see why it becomes useful. When you bring in now all the different sources, what we effectively have done is we've turned it into one large RDF graph for a lot, not everything, but a lot of cardiovascular disease. And then the question is, what can you do with it? So if you look at one chunk of, of heart diseases and say, show me all the RDF connections, you get this type of thing. And that's, what this shows is you get a hairball where the relationships, even though they're typed, it would be impossible to really track it as a one large thing. Now you can query this thing, but you'd have to know what you're querying for. So maybe you've got a couple of good schemas, but what are you going to ask for? I want to see this gene and show me all the diseases associated with it. Well, okay, but you're going to do that for every gene? That's going to take you time. Or I want to find 2 genes and see if they're related by any symptoms that they produce for the disease. You can do that. But that's only catching a piece of the snippet too. You'd like to ask 4 different things and say, is there anything in here that connects the symptoms with a common pathway that has at least 2 of the same Go functions describing the molecular process, and show me what genes are involved. And it would be nice to pin those out, pull those out of the haystack all at once. And so really the challenge of the semantic web is not just yet another query frame, but how can I find connectivity and interesting things faster? And this is a big challenge. This is search problems. Yes? Well, in fact, the slides before where you saw the 2 terms being merged, that's the disambiguation that's needed to be done. And it hasn't been done for the entire field, so a lot of us have to do it piecemeal. If that were aligned, if these were connected so you could go from phrases in medical literature directly to all the structures, it would be fantastic. We would have saved us a month easily. It really would. And that we found MetaMap did a pretty good job, but it's a problem. So that's one thing we'd like, is the alignment problem to happen. So disambiguation with gene terms is another one. So it's all over the place, clearly. But because now things are being identified cleanly with tools and things on the web and the semantic web, you can address them one at a time. They don't slip by as easily. And in fact, we've used System and Protege to even uncover problems in the pathway models. We found gaps in them because some things need to have, based on the structure, these components. And we did an inference and found 5 examples that were missing something. So you can do quality control with these tools too. So now here's a fun algorithm, which the color is terrible. You can't read it. It's a Kleinberg algorithm out of Cornell. It's a form of PageRank, all right? And this is, from what I understand, this is one of the original PageRank sources. So this is a very generic way of thinking how to sort nodes in a graph. And what we're going to talk about is graphs that are pointed to are referred to as authoritative because, like when you cite a paper, everyone cites this great paper that was done in early work in genomics. So that's the authority, and then everyone else is just referencing it. And what you have then is that a set of nodes that are being pointed to, and this is still along the way of the old web, right? Papers being referenced just through hyperlinks. And then on the other side, you have things that fan into them. You call them the hub nodes. But there's scoring that you can base on whether a lot of things are feeding into it. There's also scoring you can put on the hubs. And the reason you can do the hubs is that even though a node that gets a lot of things pointed to gets a higher score, if you have many, many of these important hubs that many things point to, and this guy points to all of them, you may judge and say that score of that hub should go up as well, especially if it cites 5 good papers on patents. Maybe it's come across a new way to integrate those things. And what happens, of course, is in RDF, it's not about who's more famous or what. It's not a prioritization based on what is the hottest topic. There are mechanisms of action. There's pathways. There's symptoms. So these arrows now have meaning that is not about what's the most familiar. It's about what's the one that causes stuff. And so the mapping problem of PageRank is a very different one in the data graph world. And as an example, you can say that a gene that points to, that is involved in multiple pathways is probably a very important gene because it will, if it's mutated, it influences a lot of pathways together. It could be very, very important. The inverse, a pathway that has many genes that participate in it isn't as interesting because most pathways have, a dozen or so genes. That's not, if it has 100, that's usually not that much more important. But it's when a gene, because the flow of information is, if a gene is mutated, it affects the pathway's function, not the other way around. So you actually can build in directive biases that follow causal relationships. And you do this for your 10 or 50 different RDF predicates. But now you apply PageRank to that. And the whole system now does a centrality analysis of all the knowledge you have on genes and the diseases. And here's just sort of a schematic view of PageRank. If you see a document that's pointed to by many other papers, and they themselves are referenced, you tend to get this sort of distortion in the scoring. If you do this now to phenotypes and diseases and genes, you can uncover some very interesting relationships. So here's an example where we took data. We queried a loci, an area of the genome that was known to be involved in cardiomyopathy. And when you start the process, you get about 200 genes that are in this vicinity. And if I now say which genes have any relationship to certain pathways, if you add only that into the prioritization, into the ranking algorithm, a particular gene that is known already to be very important, but we didn't say what it was in the system, gets up ranked to 105. So it moves up the chain. If you now include biological process information, it goes up to 47. Goes up only a little bit with molecular function. That's sort of in line with what people think about this aspect of Go. This is too specific to the type of function of the enzyme, not to its role. Compartment, where it is, that's important. So now it's up to 26. And if you add the clinical features associated with OMIM, it comes up to the top. So what this is saying is you can show using ROC curves or anything that as you add more and more knowledge of very diverse types, PageRank algorithms put up very obvious and good candidates way to the top. This has never been demonstrated before. So the difference here with other approaches that use protein interaction or just clinical features is we're using everything. And the thought is the more you throw in it, even if there's noise, it'll start to clean itself. And that's sort of what companies like Google like to say always too. So this is the first time it's being applied to data, though. This is not web pages. This is actual data and relationships and diseases. And we've also shown that if we add subjectivity, if we say there's a reason we believe in this particular phenotype is very important, we can take something that's ranked low and pull it up higher to be perhaps, as it's been shown in the literature, be the cause of a particular metabolic disorder. So there are various ways that you can extend the algorithm to sort of focus on various subfeatures. And we call that subjectivity and objectivity weighting. How do you get at the data? So when you get these candidates, do you just believe it? No. They can then be further refined. You can say, get me all the information, describe the information around that. using what are known as sparkle queries. So here's a chunk of sparkle that says, describe everything around this gene that was prioritized high. And the nice thing about the semantic web is it's already structured. It doesn't have to do any weird tabular viewing. It just pulls up this thing. Here are all the reasons why this gene came up in this rank, and we view it using an open source tool called Welkin from MIT. These are all the different Go annotations that show extreme overlap with other genes and diseases that are known to play a role in cardiovascular. So you don't just get a bunch of prioritized things that you're like, now what do I do? You actually can mine it further manually. And in that sense, it's a hypothesis generation tool. We're finding things that, we found things that are just being known, and we've also found things that haven't been identified yet, and we're keeping an eye on it. We have a group of molecular biologists studying cardiovascular disease to further uncover the relations here. The feeling is that it's not a system that gives you 100% hit, but it certainly can cut the time from going to the literature and looking for potential candidates to just a matter of days instead of months. That would prove useful. Now the thing gets more interesting. What if we include pharmacological data, like what drugs are involved in diseases and what processes? Can we find alternative treatments for a approved drug? Meaning it's already out there, you're making money. Is there a quick way to find out what other diseases it could be used for, and you can extend the patent that way very cleanly? So this is the kind of strategy pharmaceutical companies like. And so this is sort of the overall ontology that shows all the different elements, the substance, the mechanism of action. These are the things that will plug into processes that are in the biological side in terms of the biological entities, the gene, and the pathways. And so here's an example of something that was pulled out where a drug that already exists, losartan, is related to a particular gene, AGTR, that is in development of heart disorders and stuff. But we find through these associations two strong indicators for another genetic disorder known as Marfan syndrome, where it is clearly there are many very common phenotypes and mechanisms between that and the original target that's treated. So we show this because at the time we were doing it, there was an article coming out that losartan could be used to treat in early individuals various symptoms of Marfan's disease using it. So we're starting to see this thing is starting to prove useful. The problem is we've only focused on one area of cardiovascular, and we want to sort of extend this to other areas. So it involves a lot of validation with the scientists. So we're enlisting other groups to work with us and try in their favorite areas, whether it's neuroscience or cancer and stuff. But it's, the mechanism behind it is pretty much standard semantic web. Again, you can add now, once you have a structure, you can do inferencing. If you don't inference, you find these candidates that are, somewhat overlapping. But if you now put in the relationships of these things are type and hierarchy of a lot of signaling genes in the same sort of pathway, you get a different set response. So inferencing rather than just querying gives you additional refinement that you can take advantage of using semantic web. Any questions? And let's see, we're a few more minutes here, right?
That's a fun.
Okay. Well, it would be more fun if we have a two-way discussion. Clinical trials is a space that is important to pharmaceuticals, and the reason everyone here should be concerned is that's probably the number one reason why drugs are expensive. Because clinical trials will range from $200 to $500 million per drug that's going to be successful. And you have to remember when you develop drugs, there are going to be a lot that get into clinical trials that fail. So who flips the bill for that? It's the drugs that are successful. So their price goes up. And if you want things that are safe, you've got to test thousands of individuals. So there's two choices. You either find a way to get more people enlisted for less money, and one idea is do a lot of your clinical trials now in Asia. And that's what pharmaceuticals are doing. The other is two things. Don't increase the size of clinical trials, but get more information earlier that you can validate more facts specifically in focus studies with maybe only a few thousand individuals, plus a plan when the drug is marketed, if it's approved and marketed, you prove you have a good plan that follows up on any adverse events that may occur in early users. Because the real trial is what happens in the first couple of years when you have 10 million people. taking a COX-2 inhibitor like Vioxx. And you want to keep track of that. There's going to be surprises. There are going to be genetic background effects. But if you have things in place, you can deal with them then and learn from it. So there's an entire way of rethinking how we can do clinical trials more effectively. We can make them cheaper, maybe faster, and still get the same safety and benefits out of it. And we hope we can do that because that's probably the only realistic way of cutting down the cost of healthcare. The other thing is, so far the United States has been really the strong supporter of advancing drug development and innovation. We pay a good amount of money for that to advance it. And the world may not stay the same. It may become a point where the public says no more for these high costs, especially if you can go to Canada or Europe, and it's a fraction of that. So there really is an imperative to find a better way to do clinical trials and yet get as much information out of them. So this isn't showing text here, which is not, well, SDTM is a particular format. It comes out of it's called the Study Data Tabulation Model. It comes out of the CDISC standards group and is very much an XML-based model for exchanging information between hospitals and sponsors on the clinical responses of patients being treated with diseases, being treated for diseases with new drugs and dosing. It's a tabular form. Right now, companies like SAS have their own proprietary form, and SDTM is almost modeled after SAS. But there's weaknesses to any tabular model because if you try to include context, like how did you take the blood pressure of this person? Were they laying down or did they just exercise? There's no place to put it into these models easily. But if you used a triples model, it's very easy to add that metadata. So there are early discussions, and you'll see on the W3C website, there's even links to some of the early thoughts we have on taking SDTM from XML into RDF. And that's what this slide would show you here, but it's not. So we'll go on to viewing the data. And part of the semantic web problem that had been around, a lot of us said, well, we're manipulating all these things, we're querying stuff, but we don't know how to look at this data. I mean, we can look at HTML, and we can have style sheets to look at XML, but what's available for RDF? And so there are some very intriguing new technologies out there. This is out of MIT from Simile. It's called Exhibit, and it's a very, very elegant way of dealing with data that can come in a variety of forms, including RDF. And it has views. It has tabular views. So if you're a clinician, this is the kind of stuff you like to see, whether it's Excel or if it's SAS. You need to see tables and sort them. But this is actually a mashup between data from multiple sets. In fact, there's data from treatments, adverse events, demography, and polymorphisms that usually sit in different databases, but this system actually pulls it together. And then what we do is you can specify what are the different selectable facets. So most of you are familiar with faceted viewing on data sets. And so for each of the different themes here, you can say, I want to be able to see what are all the different categories, how many of them are there. And if I click on that, the whole set here gets filtered down to just that, instantly. So some people regard that as querying, but it's really a faster client-side way of refining your search and looking for patterns. So if you refine that, you can, well, I'll walk you through. I'm sort of going ahead of myself. The other thing about this data, I can look at it from another perspective. I can say, for various values of weight and the age, I can plot this stuff, right? So the same data now is a bunch of points that I should have shown the image. You can click on that, and it has the entire record attached to it. The nice thing is there's no code writing to do this. There's one little line that you include in your HTML document, and it does it for all the data. It's a very, very sweet little trick. And the same applies to any of the views, tabular or tile views, thumbnails. You can put together clinical views of all different images from the patient. And it keeps the structure of the RDF inside the memory so that you can continuously flip around all these different pivots and preserve that. And then you might say, well, I'd like to filter down to only certain treatments. And then you can see the subset for that. And then you can pivot back. So it doesn't do everything. It does 20% of what most people would say is a system should handle all the stuff that you want to do in statistics. But that 20%, this flexible, solves a lot of interesting views. And this is just a quick test. So a lot of us are hoping someone's going to go with this and make a product out of this type of approach. But it's an HTML page that just has microformat hints of how to view the RDF. That's how it works. Yes? So say that again. Oh, okay. Yes. Oh, yeah. Absolutely. Yes. Most tools of the semantic web now, like protege tools, you can plug in different inference engines. So Racer and Pellet are inference tools. If we want to get into the details, the real challenge is if most of the stuff you're representing can be described as classes or restrictions on classes, clearly T-box reasoning is very fast with inference engines. So you can do a lot of deep, looking for patterns that way. There's an interesting question, though. If you represent patients as instances, you've got to do A-box reasoning. And every system chokes at some size. A-box reasoning actually is done better with query engines, like SQL. A-box is instances. T-box are the logical class-specific relationships. Yes, okay. Right, and so the way in life science data, the closest thing you can that's similar to that, because we don't have theorems in biology. There's no theorem. We have hypotheses. So you structure a hypothesis using these elements, saying, is there anything that has this and this and this, but not this? And indeed, you can do that with both inference engines and or rule systems. So that would be defined. Finding those de novo, that's not so obvious, but what you saw with that early example of mining information and finding patterns, if you find enough examples, you could generalize. So theorem provers that have generalizers attached to them that look for what are some of the rules that pop out, you can come up with some rules and stuff. So there's a cyclic process. But most of the things in biology are, well, what is your hypothesis? You have to construct that and then throw that against the data to see if that handles. Now, there's two things. It's an open world assumption, so if something is not there, it doesn't mean the negative is true. And that's what screws up a lot of these systems. In fact, if you want to say this was tested but it was negative, you have to make that an explicit statement. And that's, again, that's a practice that not everyone follows. But, yeah. I know in the early days, I'm familiar with a little bit they've applied in medicine. There are places for that. I tend to be more on the research side, trying to find causes of diseases, for instance, and associations. And that's more of the search, query, and do statistics on. But people who need to take what's there and say, is it this or that for sure, you can use the logical structures, indeed. And most of the, if you're familiar with Racer and Pellet, they will do that type of inferencing on that. Pathway groups have attempted to do that with cause and effect modeling. So how does this jump around here? Okay, right. So here's a case where I'm looking at adverse events. These are the nasties that happen in a clinical trial. But you don't know the adverse event is due to the drug or not. Adverse event is just an event. It happened while we were testing the people, and it might have happened to the person taking the placebo. But you capture all of it. And so every adverse event has its own identifier, and you have it associated with people, and people can have 0 or many adverse events. And it happens in particular systems. If you've captured the data right, you say, what system and symptom is associated. And that's very important to get good electronic data capture. That's just starting to happen in the clinical field. But now what I can do is I can say, well, I'm interested in two kinds of events. I'm really concerned about that heart problem. So cardiovascular and blood, hemic lymphatic. So if I select those two, you'll see then the system now refines to just those individuals. You can see then those various symptoms, tachycardia, migraine, palpitation. And then you can, of course, now pivot it and put it into a plot and even ask, what are the background genotypes of these individuals? So this is, answering some, letting you to investigate some real-world issues. Does it look like semantic web? Not really. It's a table of things. The only thing you'll notice is this, it was able to grab it from multiple sources and stitch it together very quickly, and that the building of these sort of viewing rules, very, very lightweight. I don't have an example in this slide set, but it's on the website. You can take a look at it. It's very, very easy to see how this thing is structured. It takes, this view right here is only about 6 lines of code, and it's in HTML. So anyone can write HTML. These things are very easy and accessible to people at Pfizer that do clinical work, not the informaticists, the actual clinicians. And they like this. So one day, when we get the right people behind it to make a robust version of this might be sort of a nice viewing tool of the future. One of the things that makes this thing work so well is that it automatically knows to build, even if you can take data from a spreadsheet, put it into the system, and it'll convert it into this. It's actually creating identifiers, URIs, for each row in the spreadsheet. And that's a tool called Babel that does that. It's a lot of fun. Yes? Yes. So this is a clinical trials example. You'd be referring to electronic health records that are longitudinal.
Right, but we actually use this as an example, so I can modify, for example.
Yes.
So for instance, someone has an adverse effect, but that adverse effect then moves from a situation where it's mild, but maybe moves towards something that's moderate or eventually severe.
Right, because you have the dates of when the events are occurring. And I don't have the view here. If you go to the demo on the line, it's actually better than the slide presentation. You can see the timelines of these things. So it'll actually show you, whatever you selected, the subset, it'll show you the timeline of that person or group of people and what happens over time. The events occur more and more. So you can do, in this study, limited longitudinal, in where diseases are changing. That's basically, doctors want to do this to see how well you're responding or if there's something more serious here. So they do want to make sure electronic health records are smart and can be stitched together. The way it's done is that if you have, whether it's an event or more generically, you have a visit. So every visit is a node in the semantic web. And here are all the studies that were done when you visit, all the diagnostics and all the interpretations by the doctor and the dates there. Then you have another visit. You can stitch them together. And then you can sort of go click, 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 click through. You could even say, in one of these sort of exhibit views, you could say, show me my last 30 visits over the last 10 years. It's there, and you could then put a little profile. And it's very lightweight. It doesn't have to be sophisticated to do that. But some people point out semantic web is a great paper trail system. And different adverse events, imagine this was all one subject. So if you pivot that way, you say, for this given person, show me all the events or all the visits, and line them up, sort them by time. So it's a matter of this graph that I sort of described, very sort of waving my hands. You can say, just show me for this one individual, and that highlights only those elements that are affiliated with that individual. And you can view the data, the doctor could view the data in a variety of ways, just focusing on that one record. Or you can look across a lot of them. It's very fluid. And if you're in a study, remember, you're all enlisted to take one drug or another or the placebo. Now, the following the individual as a group is important. Or if you are a part of a bunch of people that got some terrible disease and are in this clinic, they want to keep track of all you as a group. So it depends how you want to pivot this graph and monitor it in real time. But for you, an electronic health record, you'd be one person with a series of visits and findings and treatments. And that would be all organized. Even if it came from different hospitals, it would be stitched together. That's the vision behind it. Yes?
Taking your different hospitals example and then exploring out further on the web as a whole, that depends on web indexers being taught to index the RDF triplet, right?
Yeah, they would all have to agree that.
The web every time you want to query something.
No, you're right. You certainly, in a robust environment medical system, it's got to be smarter. Caches, if you need to get more, you can, but there's a way to get to it somehow. There's a lot of other things. You have to make sure that the identification scheme for an individual is unified. Now, a patient record identifier is not the same thing that is your personal identifier, Because your personal identifier is maybe your blog site or who I am and my email. But to the hospital, they don't care about that. They might use it as background information. They have when you check in and when you check out. That's where they are really concerned about you. So there is this problem of which identifier do you use for yourself? Social security number or what? And there is no real good identifier number. And in fact, if you said, let's make one that's nationally used, I think a lot of people would be a little scared to do that. So there's an interesting problem of, can you use multiple identifiers to make you pretty clearly you? It's not guaranteed, but it's 99.99% you. And there's a thing called friend of a friend. It's an RDF graph. There is no identifier for it, but it has your email, it has your name, it has your affiliation, and if there's enough of this, it's pretty clear with the other ones they align. And the idea is that you do it through alignment. Let's just run through this last example. Here's a case of a knowledge base that was put together through the work of the actual interest group, the W3C, working with a variety of groups. There's a Bern network. We talked about Bern earlier, so a lot of the people from Bern are involved. But we pulled the data together, again, into an RDF representation. So this is quite ugly, but what you can see is that we can take the data that's in the various systems on genes and proteins, but we're able to link them to, font color is terrible, but this is image data from Paul Allen's Brain Atlas, nicely available on the web. So now we stitch it into the semantic web. And so they've got these great little pyramid views that you can zoom into different parts of the brain, but we can stitch it into this graph and make browsers be able to go between them very easily. So just to go through, here is the kind of query you can build across multiple diseases. You can say focus on pyramidal cells. So this is RDF a la what's called N3. You notice there's no XML in it, and thankfully not. It's just, it would make this really impossible to read. But each statement here is a set of triples. You can see, has function and, as process. It's a way of, with the question marks, those are the free variables. And the top part says this is the part of the anatomy. It's looking for journal articles that are related to it. It looks then for the genes associated with the journal articles, and it says, is the gene a signal transduction protein? And if so, can you bring me an image of its expression from Paul Allen's view? And so you can find, here are all the candidate genes and their functions. You can show it as text. But you can also then put it through various engines that can now find them on the Brain Atlas and then be able to zoom into those things. And so this is work that was done with the Science Commons in conjunction with people at, what is the group at Yale called? There's a brain research group there, that were Brain Farm. And you can vaguely see it. So this is exhibits. This is something I wrote with looking at the same data graph, but then rendering it using an exhibit template to say, pull out the image and put it right there. Get me the information from Entree on the genes, and then draw them there too. So the data itself does not live in this knowledge base, but the hooks to the images and the genes is there. So it's very easy to add that into your dynamic viewing tool, and it pulls it in together. And then I can select for various types of genes and filter through. So that once you've got the RDF and you've got these sort of front ends, it's very, very easy to make these mashups. And what's nice is that you can push this. And whatever things you've filtered on, it now saves that as a subgraph that you can send to somebody or work with in addition. So you're not just viewing dead-end information. You're capturing what you found. You can annotate it, and you can push it back into a working notebook. So it really connects the entire cycle of the research, from the collective knowledge to the investigation and the interpretation, and then saying something about it in a way that you don't lose it. You put a smart bookmark that you can share in your community. And it's just really using just the RDF behind this. This is the last thing I was going to show, which is, so where are commercial applications going with this? And there's several, but I'm doing a plug for my stuff here, actually. One of the areas that is important, of course, is to work with legacy systems. And we have a lot of databases. The mapping of that to the semantic web isn't automatic, but you can produce very nice rule systems that work with classes and objects to do that for you. And basically what happens is that everything in here now can be pointed to as an entity on the semantic web. It has a URI. Even though it only had a primary key before, it now has a URI. And you can even fetch the stuff out. So when you have this, what does it look like? Well, it looks like a sort of chemistry Web 2.0 app. It pulls the information, and it can put it in nice little HTML blocks. But if you click on the little triple up here, you'll see that it pulls up then the RDF behind it. Now, this part of the information was from the target of this compound. That's in the database. But you'll see there's stuff below it that says has annotation. That doesn't sit in the original database. So going back again, what you see you can do is you can actually, by clicking on these orange links here, you can tag and annotate them. You can put in, I think this is related to another disease, or is probably the data that's from this study might be, analyzed in regard to this particular compound. So your annotations end up being sort of hyperlinks between your databases. And that's nice, but then how do you find these links? When somebody goes to the database, they're just looking at the information of the compound. They don't know that there's a semantic web world around them. But what you can do is you can make the servers aware that there's additional information, and then you can serve that up even though the person didn't even go anywhere in the semantic web. There's this additional set of facts that are added on, saying here's what else is known in the enterprise. And it could be a simple comment, but it could be very rich model level descriptors. And this doesn't do, you don't require this to change anything in your original schema. It's universal, it's indexed throughout the enterprise, and it's accessible to a lot of query engines and search engines. In fact, the stuff you saw described before using PageRank can be applied to this. So whatever knowledge people have collectively said about between these diseases and compounds can be mined collectively throughout the enterprise. So, and it's working, remember, in legacy structured information. There's no RDF store of the chemical compounds or the genes. It's only these annotations that we manage uniquely as RDF, but we can cross-link them to anything in the enterprise. We can do the same thing to spreadsheets. This is a very simple table that was brought in that had compounds and various assays. Once it's in there, these are now unique RDF nodes, and you can actually add annotations, click and, shift-click, and put up a bunch of facts about, I need to revisit this, or this is connected to something. So you can start to add links into other dimensions from otherwise flat tables. And it's a way of preserving now the file in a more connectable URI model. So there's URIs not just for the assay, there's URIs for all the columns and rows as well as every cell. And that's generated dynamically as it's brought in and parsed. So this is just a quick sort of overview what, both spreadsheets and relational databases are accessible, and you can sort of mash them up into these formats. So I think we'll end there. The only last thing I'll do is a plug for a conference that I'm organizing with the help of Pfizer and Merck for later on this spring, March 5th through 7th. And actually, that's not spring yet. That's still winter. All right, so late winter in Cambridge. And it's a different kind of conference because usually many conferences that talk about pharmaceuticals or biotechs have some speakers from pharma, and they have a lot of speakers from the vendors. This is an invitational meeting where we've brought in some of the leading thinkers and developers in industry, in the pharmaceutical industry, as well as healthcare, to talk about what is a semantic application. What are you doing that is relevant, not just to the semantic web. We're trying to leave it open for discussion. And what still needs to be done? What are we hoping to achieve, and what is still required to happen out there? And we hope to have a very lively, open discussion that involves not just pharmaceuticals, but academics and vendors that are interested in this area to contribute on possible strategies and ways to get at some very nice, very important challenges. And so the website, you can get to there. We have an agenda that should be up by Monday, where we have the keynotes are listed there, so you can see a little bit of the basics. It's the first of its kind through ISCB. These are the guys that do, ISMB and the others. Real nice group to work with. But we'll see how this goes. It's a real fun new type of environment for open discussion of intelligent-based approaches and semantics. So thank you very much. I'll take any questions that you may have.
Actually, I have one. In the RDF graphs,
Yeah.
what's the preferred way to handle the deletion of a subject? Do you start taking out all of the relations that also reference that subject?
So the way to think of it is you have a graph in memory. I mean, it depends where it is actually residing. If it's in memory, if you pull out that node, automatically all the edges towards that node have to be clipped out too. They're gone. Now when you say, now spit this out as a bunch of triples, all those triples are gone. So it'll be as if you went through all the triples list, and anytime you saw an object or subject mentioning that particular node, the whole thing's removed. That's the effect. So that's another thing. So it's feasible to do that. It's probably not preferred. So when people do drastic changes, so if it's not monotonic, if like models can be rearranged, the preferred strategy is to create another model. And you now have what's added or removed in that. The other one, if you had a name to it, so this is named graph ideas, you basically say this is deprecated or is named this way, and this is the new one. And so you have now a chain. You can actually point to, this one takes the place of that. And that's a better, mechanism for how things advance and change. And again, then it's a better paper trail. Yeah. Yes?
Talk about how your subjects and objects can be stored in many different places now within one database. Your triples, however, is there any those must be stored in one place, or have you ever seen distributed triples?
But they're distributed too. Absolutely. And so, the example you saw up there was actually with the chemical compounds, actually was pulling information from 4 different databases. And so the triples actually, so in a database, you can say, this compound has this feature or this, element. Certainly those triples are all in one place. But imagine if you've got a join, between different sources. The join has to represent itself too as an edge. So it's going to say this element is related to that element. If the elements are outside, if I make an annotation link, then I've made a new triple saying these things are associated by common toxicity. That doesn't exist in the chemistry database or the disease database or whatever. That has been preserved in my annotation system. And so I have now a series of triples. So basically you could, if you wanted to, dump the entire RDF graph from each of the individual databases plus my annotation system. And what the system is effectively doing is it's pulling them in together and merging them dynamically. So your triples can come from multiple places. The key, what you're probably wondering is, your triples will be able to cross-connect if the identifiers for the subjects or objects are indeed the same identifiers. That is the most important thing you have to establish. Because if they're not, there's no way the system's going to know that's the same as that unless you say it some other way.
So they have to be using a common ontology in order for that to happen?
No, they don't.
Bridging ontology?
No, you simply need the same URI. So if you've got a chemical compound in 5 different databases that should be the same, the first thing you should have tried to have done is you're using the same URI for them. That might not be possible. In which case, the second level of doing it is you say that is same as that, and that you use an ontological same as term, and that is a mapping. Now, how people interpret same as varies. Some people say it's the same real-world entity, but they're different data records. So are you talking about the same as in terms of the compound as exists in the real world, or the same as is this database versus this registry? There's subtle ways of interpreting what same as means, and that's not quite agreed upon. So you have to establish that up front in your own organization.
What do you see as the major focuses for new technology coming along? What do you think is missing?
I do think the storage of RDF is taking off now. There are systems that easily handle the billions of triples and are very fast in serving them up. The group in the UK, Garlic, are doing massive amount of civil information storage and retrieval. I think that area is going to continue to get more competitive. So it's hot. The real thing that's missing is this smart way of indexing or even working with legacy systems and all those data tables you work with, you're going to have to say what is the RDF schema for that. So it has to sort of do a quick guess of what is the semantics. How that semantics maps with a semantic that comes from Stanford on gene ontologies, that's not trivial either to do. So that later stage ontological binding and association is going to take time. It's mainly not a technological problem, it's a social one. People have to agree to the terms, and is what I have in my gene database indeed what is represented by what Stanford is talking about, or not? And so we had this discussion at a meeting in Novartis. Maybe we need core parts of these things, or core ontologies, so that genes may or may not have their Go definitions, but there's a minimal thing that says why these are still, these are all genes and why they may be equivalent. That's a core system, like a minimal definition set. Yeah, and that would have to be ontologically defined, and it's the people arguing about that and coming up with a common understanding is the hardest thing. Technologically, at least because you have a URI for everything, you can say why it's the same, when is it different. You can point to it, and no one can really get confused. But the ways you link stuff is going to be more of a sociological agreement. Yeah. Oh, okay. Right. So there's a couple things. One, there is an entire uncertainty work group formed for the Semantic Web. Just started last year. The head of it is actually a guy from MITRE. I'm trying to remember his name. Lansky? Something with an L. And they're looking for good use cases. They have quite a few, but they want more. And indeed, they want to be able to put in how do you represent uncertainties? I told them in life sciences, everything is uncertain. And what's worse is people weigh things differently because it depends on your axioms or your set of initial thoughts. And so there's a whole set of arguments that I got really into, and everyone else in the room was like going, what are you talking about? In modal logic, you can describe things with pure facts. If the Semantic Web was only about truths, you'd use this knowledge representation, usually referred to as S5. There are 5 axioms that you agree to. There's a truth axiom, and that if it's a negation of that, it's a non-truth, and blah, 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 the usual stuff. And it's Lasky? Okay, thank you. What's his first name? Ken Lasky, thank you. I think his wife is also serving as a chair on that, if I remember correctly. So the problem in biology is there are many things that eventually will probably be untruths, but we don't know this yet. And you want to say them. That's what a model hypothesis is. You can only disprove things. You can't prove them in biology. So you use a form of logic called KD45. KD45 is 2 of the premises in S5 are changed. So I forgot, you can look at the logic equation if you like looking at those things. But it basically says an untruth is acceptable as long as it's not been proven yet to be untrue. See what that means? That if something is indeed untrue, but you don't know it hasn't been proven to you, you can hold on to it. And it makes scientific sense. If someone shows you enough facts that says it can't be true, now you got to drop it. But that means over time, what is true and what isn't, or viewed as being evidence, is going to change. And so KD45 models need annotations and timestamps. And that's an interesting challenge for areas like life science. I've been trying to advocate that for the health field as well. So every annotation is assuming a KD45 logic. There's very few things you can say are absolute facts. Even if something comes off of a machine, maybe the machine had a bug in it, There's not many things in biology you can say is an absolute fact. But there's some things that you're willing to believe more strongly than other things. And hypotheses, you might be 50-50, it'll stay, it'll go. And if you can associate uncertainties and weights to that, many people are interested in that, especially for predictivity of disease and outcomes. That's where it becomes really important. Now you need the numbers. So indeed, that's where it starts getting into real computational work. Yeah?
You made a number of references to annotations, and then now there's the issue of trust. How do you feel about reification of an RDF, the whole idea of actually annotating one of your RDF triples to say that this fact may or may not be true, or I'm the person to put this in?
Right. So there's a group of people that really, everything I add on to this thing, especially an annotation is timestamped with my name. So when I show those annotations, it's clear who said that and when. And what the trick is, in my example, those annotations are named graphs. That means they are reifications. I only include them into the scheme of things if I'm willing to accept, the responsibility of trust in these authors. So that means is there's a way to get a lot of RDF, but the annotations, they don't reify themselves until I say yes, 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 no, no, no. Then they get turned into triples. They get added, and then I can compute with that. And the advantage is I can have 2 different views of how a disease works, and I can try group 1's approach, and then remove it and try group 2's approach, and each time I'm doing data mining and inference with those different sets. And now I can do comparisons. So that's the way to do, comparative modeling between different logic structures in RDF. You just switch one on and switch one off, and it's easy to do with tools like Jenna, because Jenna has different model graphs that you can load. So you can load one with this amount of data and assumptions, the other one with a different one, and you can run the two things in parallel and see what's diff between them.
Is it common?
Yeah, so name graphs have been promoted for a while, and most of the storage systems actually support multiple models. Oracle does this too. So it's again, it's a matter of practice. But that's how you handle annotations, and you don't just trust them. Even you don't trust your own. You might have different ideas in your own self, between this version of the hypothesis and another. So you want to be able to switch between them, and that means instantiating different versions and comparing them in different spaces. That's it's a very important point to think about for research. Yeah. Well, guys, thanks for staying on Friday. It's late.
Thank you. Thank you.